This is a tutorial on finding the cross product of two vectors. Finding the cross product of two vectors is a different way of multiplying two vectors. Now, to find the cross product of two vectors, we're going to have to know how to calculate the determinant of a matrix. So let's review that very quickly. If I wanted to take the determinant or find the determinant of this matrix x1, y1, x2, y2, then I take x1 and I multiply it by y2 in this downward diagonal. So x1 times y2. Then I go back the other direction and I take y1 times x2 and I multiply them together and I subtract that from the product of x1 and y2. So if I have the matrix 1, 2, 3, 4, and I wanted to find its determinant, I would take 1 and 4 and multiply them together, and then I would subtract 2 and 3 multiplied together. The determinant of this matrix is equal to -2. So let's find the cross product of this matrix. To do so, we would take 4 and 4 and we would multiply them together. Then from that product, we would subtract 7 times -2. So 4 times 4, and then we subtract 7 times a -2. So 4 times 4 is 16, and then we're subtracting 7 times -2, which is a -14. Now we're subtracting a negative, so that's the same as adding. And the determinant of this matrix is equal to 30. So now let's try taking the determinant of a 3 by 3 matrix instead of a simple 2 by 2 one. Now there's two basic methods for doing this. The first one is to take this 3 by 3 matrix and turn it into several 2 by 2s. The first thing I do when I use this method is I make this x1 positive, I make this y1 negative, and I make this z1 positive. Then I start with my x1 and I ignore both the row and the column that are next to x1. What I'm left with is y2, z2, y3, z3. I take this x1 that I've blanked out or crossed out and I multiply it by the 2 by 2 determinant of y2, z2, y3, z3. Next, I move over to the y1, and I ignore everything next to and below the y1. Now remember, this y1 was negative, so this is minus y1, and then I multiply that by the 2 by 2 determinant x2, z3, z2, x3. Then lastly, I take this positive z1 and I cross out everything next to it and below it, and I multiply z1 by the determinant x2, y3, y2, x3. So my determinant of this 3 by 3 matrix would be equal to x1 times y2, z3 minus z2, y3 minus y1 times x2, z3 minus z2, x3 plus z1 times x2, y3 minus y2, x3. Whatever these numbers are, x1, y1, z1, x2, y2, z2, x3, y3, z3. Plug them all into this, and you'll find the determinant of this 3 by 3 matrix. Now, the other method for finding the determinant of a 3 by 3 matrix is a little bit different, but you'll end up with the same answer. The first step is to take the first two columns of your 3 by 3 matrix and rewrite them next to your matrices. Then, starting at x1, draw a line diagonal until you hit the bottom of your matrices and multiply all three of those numbers together. So x1, y2, z3. Add that to another row or another diagonal of numbers being multiplied together. So y1, z2, x3. Then add that to the next diagonal, z1, x2, y3. Now that we've hit the bottom and the end of our columns and rows, now we go back the other direction. Draw a diagonal going down and to the left. So we'll multiply y1, x2, and z3. But since we're going backwards this time, we're going to subtract this product. And then we're going to subtract the product of the next diagonal, which would be x1, z2, y3. And then one more. We're going to subtract z1, y2, and x3. So whenever you're going to the left and down on these diagonals, you subtract your product. And whenever you're going to the right and down, you add your product. All 6 of these terms together will get you the same answer as method 1. Now, you don't have to memorize both methods. You can use one or the other. Again, they'll both give you the same answer. So let's try practicing this. Here we have a matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. We want to find the determinant of this 3 by 3 matrix. Using method 1, I first look at my first row, and I make my first number positive, my second one negative, and my third one positive again. Next, I start with the 1, and I ignore all the numbers below and next to it, and I take that 1, and I multiply it by the 2 by 2 matrix that's left over. So 5, 6, 8, 9. Next, I move over to my 2, which I have made negative, so minus 2, and I multiply that by the 2 by 2 matrix I create by ignoring everything next to and below this 2. So 4, 6, 7, 9. Then lastly, I take this positive 3 and I multiply it by the 2 by 2 matrix I create when I ignore everything next to and below that 3. So 4, 5, 7, and 8. Now I need to find my 2 by 2 determinants. So I have 1 times 5 times 9 minus 6 times 8. And then minus 2 times 4 times 9 minus 6 times 7. And then plus 3 times 4 times 8 minus 5 times 7. So what I have is 1 times a negative 3 minus 2 times a negative 6 plus 3 times a negative 3. This is equal to 0. So the determinant of this matrix is equal to 0. Now let's try our second method. And let's make sure we come up with the same answer. Using the second method, I take my first two columns and I copy them over next to my matrices. Then I multiply in a downward and to the right diagonal. And everything I multiply along these diagonals I add together. So this is 1 times 5 times 9. And I add that to 2 times 6 times 7. And I add that to 3 times 4 times 8. Then I go in the other direction and I multiply 2 times 4 times 9, 1 times 6 times 8, and 3 times 5 times 7. But since I'm going in the other direction, I subtract all of these multiplications. So minus 2 times 4 times 9, minus 1 times 6 times 8, and minus 3 times 5 times 7. 1 times 5 times 9 is 45. We're adding that to 2 times 6 times 7, which is 84. Adding that to 3 times 4 times 8, which is 96. And then we're subtracting 2 times 4 times 9, which is 72. Subtracting 1 times 6 times 8, which is 48. And subtracting 3 times 5 times 7, which is 105. Once again, this is equal to 0. So it doesn't matter which method you use, memorize one of them. So when you need to find the determinant of a 3 by 3 matrix, you will come up with the correct answer. So now let's talk about finding the cross product of two vectors. Finding the cross product is a different way of multiplying two vectors together. When we do it, we say it's vector r crossed with vector s, if this is vector r and this is vector s. Now when you're crossing two vectors, you should always get a vector as an answer. Remember, when you find the dot product of two vectors, your answer is always a scalar. But when you find the cross product of two vectors, your answer is always a vector. Now, to find the cross product of these two vectors, r and s, you create a matrix. In the first row of your matrix, you put the three different directions: the I hat, the j hat, and the k hat. This is the amount, or you can think of the unit vector in the x direction, the amount our vector moves, or the unit vector in the y direction, and the amount our vector moves, or the unit vector in the z direction. Then in the next row, we take our first vector, which is r, if we're crossing r with s. Underneath the I, we put the amount r moves in the x direction, so 3. Underneath the j, we put the amount r moves in the y direction, so -2. And underneath the k, we put the amount it moves in the z direction, so 4. Now we're crossing r with s, so underneath the 3 goes the amount vector s moves in the x direction, which would be a -4. The amount it moves in the y direction, which is 3, and the amount it moves in the z direction, which is a -2. Now that I've created this matrix, to find the cross product of these two vectors, I just find the determinant of this matrix. Now you can use either method. I'm going to use method 1. I make this a positive I, a minus j, and a positive k. Then I take and I ignore everything below and to the right of the I. I take this positive I hat and I multiply it by my 2 by 2 matrix that's left So negative 2, 4, 3, and negative 2. Then I take this negative j, and I multiply it by whatever's left after I ignore everything next to it and below it. So the matrix 3, 4, negative 4, negative 2. Then I go to my positive k, and I multiply that by everything that's left when I ignore everything below it and to the left of it. So the matrix 3 minus 2, negative 4, and 3. So what I have left is I multiplied by the determinant of this 2 by 2 matrix, so negative 2 times negative 2, minus 4 times 3, and then minus the j multiplied by the determinant of this 2 by 2 matrix, so 3 times negative 2 minus 4 times negative 4, and then plus k times the determinant of this 2 by 2 matrix, so 3 times 3 minus negative 2 times negative 4. Negative 2 times negative 2 is a positive 4. 4 times 3 is 12. Positive 4 minus 12 is a negative 8. So I have a negative 8i. 3 times a negative 2 is negative 6. Minus 4 times negative 4, which is a minus 16. When you subtract a negative, you add. So this is going to be a positive 10. But I have a positive 10 multiplied by a negative j. So this is going to be a minus 10j. 3 times 3 is 9. Minus negative 2 times negative 4 is a positive 8. So 9 minus 8 is 1. 1 times k, so plus 1k. So r crossed with s would be equal to negative 8i minus 10j plus 1k. This is a vector, which is what we should get when we find the cross product of two different vectors. So this is our solution, and that's how you find the cross product of vectors. Now there are some properties of the cross product that you should be aware of. If you ever cross a vector with itself, say vector s crossed with vector s, that's always equal to 0. Now the order of a cross product is important. If you cross r with s, that's different than crossing s with r. The only difference is this negative. Whatever your answer is when you cross r with s, if you accidentally cross s with r, you'll end up with the same vector, it's just traveling in the opposite direction. It's multiplied by this negative 1 scalar. Now if you multiply a scalar, or you can think of that as a number, by the cross product of two vectors, that's the same as multiplying one of the vectors by that number, and then crossing it, or you can multiply the second vector by that number and cross it with the first vector. What's important to realize is we're taking the cross product of two vectors and multiplying it by some number. This is not distributive because these are all just different types of multiplication. Here we have vector multiplication, and then we have a vector times a scalar. So don't multiply that scalar or that number by both vectors before you cross them. Just do it to one or the other. Now if you want to multiply or cross a vector with the sum of two vectors, this you can distribute because you're multiplying two vectors that are being added together. So the cross product of r with n plus s is the same as r crossed with n plus r crossed with s. This is distributive because of this addition. Now when we find the cross product of two vectors, these two vectors, they create a plane. Here I have vector A and vector B. And if you can imagine, there is a plane of points between these two vectors. When you find the cross product of these two vectors, you're finding the vector that's perpendicular to this plane, or to both of these vectors. If I cross A with B, the vector that I get as an answer is perpendicular to vector B and to vector A. Now if I cross B with A instead, remember that's the negative of this vector, so I would end up with a vector that's just going in the opposite direction. This is B crossed with A. Now since the cross product of vectors A and B is always perpendicular to both vectors A and B, there's an easy way to determine what direction the new cross product vector is going. This method is called the right-hand rule. If you take your right hand and you put your pointer finger so it's pointing in the direction of vector A, and then you take your middle finger or the rest of your fingers and point them in the direction of vector B, then the direction your thumb is pointing will tell you what direction the cross product of A and B is pointing. So if I want to know what direction vector A crossed with vector B is moving, I can use the right-hand rule. I put my pointer finger in the direction of vector A. I take my middle finger or the rest of my fingers and point them in direction B. My thumb should be pointing up, and that means that A crossed with B would be moving in an upward direction. Now here I'm trying to represent a three-dimensional area, which is hard to do on a flat screen. So let's try practicing the right-hand rule. Let's find the direction that A crossed with B is going and the direction B crossed with A is going. Now if we're going to use the right-hand rule and we want to find out what direction A crossed with B is going, well, A is my blue vector here and B is my red one. I put the pointer finger on my right hand in the direction of A. I put the rest of my fingers in the direction of B, and my thumb should be pointing directly into the screen. So the vector that we get when we cross A with B is a vector that's going directly into the screen. Now if I want to cross B with A, I put my pointer finger in the direction of B, the rest of my fingers, or at least my middle finger, up in the direction of A, and my thumb should be pointing directly out of the screen. So B crossed with A is going in the opposite direction, and that vector would be coming out of our screen. Now, if you ever want to find the magnitude of the cross product, well, the magnitude of a cross product is always equal to the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them. Now, depending on what kind of information you're given, it may be easier to use one or the other of these equations. Now, if I take the cross product of A and B, I set up my 3x3 matrix. I put my I, my J, and my K in the top. Then the amount it moves in each direction, so 4, -3, and 6. And then my second vector, 1, 4, and -4. And I find the determinant of this 3x3 matrix. Now I'm going to use method 2 this time. I recopy my first two columns, so I hat 4, 1, j, negative 3, and 4. Then I multiply I times negative 3 times negative 4 plus j times 6 times 1 plus k times 4 times 4. And then minus the diagonals coming back the other way. So j times 4 times negative 4 minus I times 6 times 4 minus k times negative 3 times 1. So this becomes a positive 12i plus 6j plus 16k plus 16j, because negative 4 times 4 is a negative 16, but then times a negative j makes it a positive 16j, minus 24i, 6 times 4 times a negative I, and then negative 3 times 1 is negative 3 times a negative k, so positive 3k. Combine our like terms, we have 12i and a negative 24i, which is a negative 12i, a 6j and a 16j, which is 22j, and a 16k and a 3k would be 19k. So this is my cross product. Now I want to find the magnitude of that. The magnitude of my cross product is equal to the square root of the amount it moves in the x squared, so 12 squared, plus the amount it moves in the y squared, so 22 squared, plus the amount it moves in the z squared, so 19 squared. Now this 12 is negative, but it doesn't matter because I'm going to square it and end up with a positive number. This is all equal to the square root of 989, which is approximately 31.45. So finding the cross product of A and B, and then finding its magnitude, I came up with the square root of 989. Now let's try calculating the magnitude the other way. Let's find the magnitude of vector A, vector B, and then the sine of the angle between them. First we'll find the magnitude of vector A. That's equal to the square root of 4 squared plus negative 3 squared plus 6 squared. It's the amount it moves in the x squared plus the amount it moves in the y squared plus the amount it moves in the z squared. That means the magnitude of vector A is equal to the square root of 61, which is approximately 7.8. Now we need to find the magnitude of vector B. That's equal to the square root of the amount it moves in the x squared, so 1 squared, plus the amount it moves in the y, so 4 squared, plus the amount it moves in the z, negative 4 squared. So the magnitude of vector B is equal to the square root of 33, which is approximately 5.7. Now I just need the sine of the angle in between them. Well, I can use the dot product to find the cosine of the angle in between them. The cosine of the angle between these two vectors is equal to vector A dotted with vector B divided by the magnitude of vector A times the magnitude of vector B. So I got to find the dot product. Vector A dotted with vector B. Well, when we find the dot product, we take their x values and we multiply them together. So 4 times 1. And we add that to their y values multiplied together. So negative 3 times 4. And we add that to their z values multiplied together. So 6 times negative 4. This is equal to negative 32, which means the cosine of the angle between these two vectors is equal to negative 32 over their magnitudes multiplied together. So the square root of 61 times the square root of 33. That means the cosine of theta is about negative 0.713, and that theta is approximately 135.5 degrees. So that means the magnitude of vector A times vector B should be equal to the magnitudes of both of our vectors. So the square root of 61 times the square root of 33 times the sine of our angle, so the sine of 135.5 degrees. This should come out to be about 31.45, and this is exactly what the square root of 989 is equal to. So if you ever want the magnitude of the cross product of two vectors, you can either find the cross product and then find the magnitude, or if you know the angle in between these two vectors, it's probably easiest to take the magnitude of each vector and multiply it by the sine of that angle. Now, because the magnitude of the cross product of two vectors is equal to the magnitude of the first vector times the magnitude of the second vector times the sine of the angle in between them, we can use the cross product of two vectors to find the area of a parallelogram. Now, when I want to find the area of a parallelogram, I find the length of its base and I find its height. So area is equal to base times height. Now, if I have two vectors, I'll call this one A and this one B, then these two vectors kind of create a parallelogram. If I draw another B vector over here and another A vector up here, I have a parallelogram. Now the length of this vector A is the length of the base of my parallelogram. So the length of B is equal to the magnitude of vector A. Now this side of my parallelogram has a certain length, and that length is the magnitude of vector B. If I want to find this height, this value of h, well, this length of vector B and this height, these create a 90-degree triangle. So I can use trigonometry, and I can say that the height of this parallelogram is equal to the length of my hypotenuse, which is the magnitude of vector B, times the sine of this angle. Side opposite, so sine of that angle, which is the angle between these two vectors. If I plug this in for the base and this in for the height, I end up with this equation here. The magnitude of vector A times the magnitude of vector B times the sine of the angle in between them. Now, if I knew the components of vector B and vector A, I could just take the cross product of them, and I would end up with the area of my parallelogram, because the magnitude of their cross product is equal to the magnitude of vector A times the magnitude of vector B times the sine of theta. So I take the cross product, and then I take the magnitude of that cross product, and I have the area. So let's use the cross product to find the area of this parallelogram. Here I don't know the angle in between, I don't know the length of each side, but I'm given vectors that create the dimensions of this parallelogram, vector A and vector B. Now instead of using the two sides and the side of my angle, I'm just going to find the cross product of these two vectors. And then I'll find the magnitude of that cross product. Now the cross product of my two vectors, I have to build my matrices. The top row is I, J, and K. I'm crossing A with B. So the amount A moves in the X direction, well, there is no I hat here, so that's 0. I got 10 in the Y and 2 in the Z. Vector B moves 4 in the I, or 4 in the X, 3 in the J, or 3 in the Y, and 1 in the Z, or 1 in the K. Now to find this cross product, this time I'm going to use method 1. I make this a positive I, a negative J, and a positive K. Then I take my positive I and I multiply it by the matrices, or the 2 by 2 matrices that's left over when I ignore everything below and next to my I hat. So 10, 2, 3, and 1. Then I take my minus J and I multiply it by the 2 by 2 matrices that's created when I ignore everything below it and next to it. So 0, 2, 4, and 1. Then I take my positive K and I multiply it by the 2 by 2 matrices that's left when I ignore everything next to it and below the K. So 0, 10, 4, and 3. So then I take my I and I multiply it by the determinant of this 2 by 2 matrices. So 10 times 1 minus 2 times 3, and then minus my J times the determinant of this 2 by 2 matrices, so 0 times 1 minus 2 times 4, and then plus my K times this determinant, so 0 times 3 minus 10 times 4. 10 times 1 is 10, minus 2 times 3, which is 6. This is a 4i. 0 times 1 is 0. 2 times 4 is 8, so I have a minus 8 and a minus j. That's a positive 8j. 0 times 3 is 0. 10 times 4 is 40, but we're subtracting it, so this is a minus 40k. So this is my cross product. Now if I want to find the area of this parallelogram, I need to find the magnitude of this cross product. So the magnitude of A crossed with B, that's equal to the square root of the amount it moves in the x, which is squared, so 4 squared, plus the amount it moves in the y, which is squared, so 8 squared, plus the amount it moves in the z, which is also squared, so negative 40 squared. That means the magnitude of vector A crossed with vector B is equal to the square root of 1,680. That also means that the magnitude of vector A times the vector B, or crossed with vector B, is equal to approximately 41. A little bit less, but very close to 41. Which means the area of this parallelogram is approximately 41. Or you can say the square root of 1680. So now that we know that we can use the cross product, or at least the magnitude of the cross product, to find the area of a parallelogram, that completes the tutorial on the cross product of two vectors.